Hello everyone, here we'll be discussing chapter 8.3, which is called the vectors in the plane. Now this discussion will be quite different than what we're used to so far, but there's a lot to discuss, so let's just kind of talk and hopefully get used to the language here. So we say that a vector is a directed line segment, usually denoted by an arrow like this. So there's an endpoint and a start point and an end point. Usually this is what is called the initial point, and here would be the terminal point. So we usually say a vector goes from one point to another point in two-dimensional space. You can also talk about three-dimensional vectors in 3 space, and actually even beyond that. But the discussion here for 8.3 and even 8.4 will only be in two, in fact for the entire class, will only be two-dimension vectors. Right. So now we label this as PQ if it goes from point P to point Q. So the arrow on top denotes the vector, and it's the vector from P to Q, point P to point Q. The magnitude is, we have this kind of double absolute value notation, which denotes magnitude, which is just the length of the line segment. And then I go on to say that any two vectors with the same direction and magnitude are actually equivalent vectors. What this means is you can have some vector here and some other vector over here, as long as they have the same direction and the same magnitude, which they appear to have actually, they're equivalent vectors. In fact, very often it is thought of that these float around. So if you can float one around to the other so that they match exactly, then they're the same vector. So that's one way to think of it, is that a vector is just a particular magnitude and particular magnitude and direction, you could say, so angle and length in two-dimensional space, so you can just move around freely. So it's one way to think of it. Usually we write lowercase u, v, and w with arrows on top to represent the vectors. So this is kind of a more specific, older notation, I guess. But eventually we're going to use this notation to kind of write less, basically. This is for more geometric, but this is more algebraic, I guess you can say. Now the component form of a vector v is equal to this. So it looks kind of like a point. In fact, really this represents the terminal point if the initial point is the origin 0, 0. So where the vector v goes from the point 0, 0 to the point v1, v2. So just to give you a visualization, something like this. So let's say v1 is here, v2 is here. So it's the vector that goes from the origin to that point. So we're kind of standardizing the form so we can write this so-called component form. So we're standardizing the vectors so that their initial points are at the origin. All right. So now we want to write, for this example, we want to write the component form and find the magnitude of the vector that goes from this point to this point. And that's not very difficult to do. Notice that we don't actually have from 0, 0 to this, or from 0, 0 to something, but remember that all vectors that have the same direction and magnitude are equivalent. So what we can actually do, believe it or not, is write v for our vector, and its magnitude will be the difference between the x values. And it actually doesn't matter which one we go from. Actually, no, it does matter. Because we're going from this to this, so we're going to do the second one minus the first one, comma, the second one minus the first one. So this may sound a little strange, but I'll try to justify this the best I can. Now notice what we get as a result here is a -5, comma, +12. So I'm saying this is our answer. Now, again, to justify this, we would have to, plot things on the plane. So now 4, -7 is about over here. If that's +4 on the x-axis. And let's say that's -7 on the y-axis. -1, 5 is way up here. So it's not super to scale, but it's kind of close, I guess. Now notice, in reality, if we were to move things, so we're going from this point to this point. I'm trying to draw a straight line there. It's okay. So this is our initial point. So now what we're saying here is that if we were to move this vector up so that it's over here, this makes sense because notice the endpoint looks like it'll be a -5, and the y value for the terminal point looks like it'll be about +12. And if you want to kind of verify that more carefully, you can. But the reason why this works is because the vertical distance here is the same as the vertical distance here. and same for horizontal distance. Though we find that, of course, just taking the difference of the y values to find the total vertical distance, difference of the x values to find the total horizontal distance. So this is completely legitimate, and I box that. Now, to find the magnitude, we have to use the distance formula. Now, you could use these points, but let me just tell you right now that if you have a vector that's written in component form, you can actually always find the magnitude by taking the following. So the magnitude here, hopefully I have space for this. So the magnitude of v is equal to the square root of the sum of the squares of its components. So negative 5 squared plus 12 squared. And notice that's 25 plus 144, which is 169. The square root of 169 is 13, so the magnitude is 13. And in fact, you can kind of justify that here as well. Really what we have is a right triangle, so we can use Pythagorean theorem. We have this triangle whose horizontal length is 5 and whose vertical length is 12. So by Pythagorean theorem, its hypotenuse must be 13. So, right. So I'll have to kind of summarize that in a bit, just so we have an understanding of how we're doing these things, but we see them through this example. So let me summarize that right now, and then we can move on with some more ideas. Right, so here I've summarized basically what we saw in the previous example. The component form of the vector PQ, where P is the point P1, comma P2, and Q is the point Q1, comma Q2, that is, let's call it vector V, in component form, is Q1 minus P1, comma Q2 minus P2. So again, we're just taking the x value subtracted. We're doing the one we're going to minus the one we're coming from for the x values, and then similarly for the y values. Okay. The magnitude then of a vector in component form is merely just the square root of the sum of the squares of its components. And now we have these so-called special vectors. There's the zero vector. The zero vector is denoted 0 with the arrow vector hat on top of it. And this is the only vector whose magnitude is 0. Okay. A unit vector, let's call it u for unit, is a vector whose magnitude is 1. So these are just kind of special names for those vectors that have those magnitudes. But there are infinitely many unit vectors, but there's only one zero vector. So that's kind of something to think about. Now, these next two things are definitions. They're not like theorems or anything. They're true because we say they're true. Okay. There's a little bit of justification, but let me just describe it like this. For vector addition, if u is the vector u1, comma u2 in component form, and v similarly is v1, comma v2, then the vector u plus v, so adding these two vectors gives you a new vector whose components are the sum of the x components, comma the sum of the y components. So literally just component-wise addition. Now the reason why this is true, we're kind of trying to go from the end point of one to the terminal point of the other. So the initial point for one to the terminal point of the other. So if this is the vector u, and we have another vector v, remember that we can move them around freely. So if we move v so that its tail touches the tail end touches the head end of u, let's say like this. So I'm just kind of moving v around so that they form like this and they connect. You could similarly put u on top of v, it doesn't really matter. And what happens is the measurement of this diagonal going from the most tail point to the most end point, this red vector here is the vector whose component form is u plus v. So that's what this definition entails, and that's what it gives visually. Scalar multiplication is a little different. Basically, this is stretching out a vector by a certain value, certain scale, you can say. And notice that the direction will not be affected, only the magnitude. So here we say if u is the vector u1, comma u2, and k is a scalar, meaning just a number, not a vector, then k times u, the scalar k times the vector u, is just multiplying each component by k. This is a little harder to draw, but if k is 2, for instance, then it'll just literally double u. So if u is, let's say this guy here, then 2u would be the same direction, only double the distance. And you can do, of course, 3 times u, triple the distance, or 1.5 times And again, k can be any real number. So I hope that's okay, but remember k is a number versus u would be a vector. So now let's take a look at some examples of these, and then from there we'll look at some properties. Okay, so in order to talk about this next example, there's something I quite haven't spoken about from the previous definition of addition, and that is the definition of subtraction. So what I'm going to say here is that we define subtraction to be the first one plus negative the second one, where negative a vector is just the scalar -1 multiplied by that vector. Because -1, of course, is a scalar, and then you can just go from there based on the definitions from addition and scalar multiplication. So that's the one thing you need to talk about, of course, before we begin this. But now, beginning this problem, this example, we're given the vector v is -2, 5, and w is equal to 3, 4 in component forms. To find 2v, that's just scaling 2 into the vector to -2, 5. So that's 2 times the first one, which is -4, comma 2 times the second one, which is 10. There we go. For this one, we have w is given by, of course, that's 3, 4. And then to scale -1 into the vector -2, comma 5, all we need to do is multiply each component by -1, hence changing their signs each. So we'll end up getting 3, 4, which is w, plus -1 scaled into -2 and +5, change their signs to +2, -5 now. And now to add these two vectors, remember we add component-wise. So we're going to add this 3 to this 2, and this 4 to this -5 for the second component. So we'll end up getting 3 plus 2 for the first one, and then 4 minus 5, which is -1 for the second component. And there we go. All right, so what about v plus 2w? Well, let's see. So v again is -2, comma 5, okay, plus 2 times 3, 4. Now 2 times 3, 4, yeah. So 2 scaled into 3, 4 gives you 6, 8. So the first vector stays the same, -2, 5, and the second one is now doubling each component, which is 6, 8. And then again, adding component-wise, the first added to the first, comma the second added to the second, gives us -2 plus 6 is 4, comma 5 plus 8 is 13. So this is 4, comma 13 for this third part of this example. Great. And now I've listed some properties that involve addition, maybe subtraction, no, it's mostly addition, and scalar multiplication. So there is and a lot of them are kind of carried over from just the way we define addition. So there's a lot of addition properties and multiplication properties that we'll kind of see come up a little bit. So given that u, v, and w are vectors and c and d are scalars, then the following hold. The following 9 kind of 10 properties hold. So the first one here is commutativity of addition. So adding in the order will result in the same vector. And then we have this associativity, meaning that if you add 2 vectors first and then add that to a third, it would be the same result as adding 1 vector to the sum of the last 2 first. Adding the vector 0 to any vector just gives you back that vector. And adding a vector to its negative, which we know is just -1 scaled by that vector, will result in the 0 vector. Multiplying a scalar to a scalar times a vector is the same thing as multiplying the scalars first and then scaling that to that vector. And these two here are distribution of scalar multiplication over addition. So we can distribute the scalar multiplication over adding scalars, and we can also distribute scalar multiplication over adding vectors now. And these are 2 and 1. This basically just says the scalar 1 times a vector is just back to the same vector, and the number 0, the scalar 0 multiplied by a vector is 0, the 0 vector. That was a typo. There we go. So the last one here says that the magnitude of a scalar times a vector is the absolute value of that scalar times the magnitude of the vector. Now the reason why we need the absolute value actually is that if you recall the way we define magnitude, it's the positive length. So if the scalar is negative, it's not going to fly because our length has to be a positive value. And in fact, if you were to actually apply this property in general, you'll see that when you square the components of this scalar multiple of this vector, you actually end up scoring c. And if you have c squared in both components that are squared and then added inside that radical, you can pull c squared out of the inside terms, and then furthermore pull c squared outside of the radical as just c, but that only works if c is positive, so hence we get an absolute value. That detail is a little hard to just explain without writing, but we may see this actually creep up on us quite a bit. So more on this later. And in fact, a lot of these properties we'll kind of see, and it'll bring up as we go along, of course. So now we're going to look at a few examples that may involve these, and also we'll now be discussing on how to actually find a unit vector given any vector. Right, so for this next example, we're given these two vectors and we want to find the following magnitudes that involve scalar multiples, just so I can show you that last property I was discussing. Now, of course, if you just actually do it out, I didn't really give us too much space here, but if you actually just do it out, 2 scaled into u is just going to be 2, 6, of course, like that. And to find the magnitude of 2, 6, remember that's just the square root of the sum of the squares of the components. And then that's really just 4 plus 36. And notice that 4 plus 36 is 40. So you could write radical 40 if you want. But of course that simplifies, since this is 4 times 10 and the square root of 4 is 2. This is 2 radical 10. Now I didn't actually apply any properties at all here. I just kind of did it straight up, so to speak. But where the property applies is that this 2 can pop out of the magnitude. Since it's positive 2, we don't need to worry about absolute values because it's the same, because it's positive. And really, if you look at 1 and 3 and square those, you get 1 and 9. Add those, you get 10, so it's 2 radical 10. So if we try to apply that property here then, we can pull negative 5 out, but as a positive 5, because it's the absolute value of negative 5, times the magnitude of the vector u, which again is 1, 3. Now we already know what this is. This is just radical 10, because 1 squared plus 3 squared is 10. Inside the radical is radical 10. Now the reason again why it's absolute value of negative 5 is because if you scaled in negative 5 into these, you would get negative 5 and negative 15. When you square those, well, you get 25 and 15 squared is 225. So I'm trying to see it in my head, but if you add those, you get 250. 250 is 25 times 10. The square root of 25 is 5, so 5 comes out. Now that'll always happen because when you square a negative, it's positive anyways, which is why we need the absolute value for that to pull it out of the magnitude. So just remember, magnitudes are always positive. That's the best way to do it. That's the best way to think of it, really. So if you pull out a number and it's a negative you're pulling out, it'll always come out as a positive, kind of outside of the lines of magnitude. They have to come out as an absolute value as a result. Okay, so that wasn't too bad, just kind of based on our discussion here. Similarly here, this is the absolute value of 3, which is just 3, times the magnitude of v. Now to find the magnitude of v, all we need to do is just square each of these. So that's going to be negative 2 squared, which is 4, plus 5 squared is 25. So that's really 3 radical 29, which doesn't simplify at all as a radical. Just stays like that, actually. And now I say the following, which is a little bit different. So to find a unit vector in the direction of a given vector v, we use the following process. So the unit vector u is the vector v divided by the magnitude of v. So basically you multiply by 1 over the magnitude, the reciprocal of the magnitude, which gives you v. We'll multiply by v. Now why this gives you a unit vector is not too hard to explain. Basically it's because of this idea here actually. If you were to take the magnitude of u, since this is a scalar, its absolute value comes out, but then notice that the magnitude of this will just be, well, this denominator, they cancel and you end up getting 1. So that's not too hard to see, but we're actually going to see it with an example here. And we're going to find the unit vector whose direction is the same as this vector v, that's actually negative 2, 5 that we had from the previous one of the previous examples. So let's see if we can do this. So according to the direction I've just given us, our unit vector u is going to be the vector v divided by the magnitude of itself. So the vector v is negative 2, 5. Its magnitude, as we saw over here, is just radical 29. Remember, this 3 was not a part of v actually. So the radical 29 part is the sum of the squares of the components inside the radical. So really this is 1 over radical 29. And this is actually the answer. Now we can verify this by taking its magnitude. So let me just say verify. So to verify this, let's take the magnitude of u. Since u is equal to 1 over radical 29 times negative 2 comma 5. Then the 1 over radical 29 part is a scalar. We can scale it out of the, or pull it out of the magnitude. So we end up getting the absolute value of 1 over radical 29, which is itself because 1 over radical 29 is positive, and then that's multiplied by the magnitude of the vector negative 2, 5. But we already know that this magnitude is just radical 29 itself, so we end up getting 1 over rad 29 times radical 29. And notice, of course, they cancel just like I said they would, and we end up getting 1 as a result. Now, the only thing that I think we should do that I haven't actually done here, which all of this work is still valid, is to rewrite this rationalized. So multiply top and bottom by radical 29 gives us radical 29 over 29 multiplied by this vector. And you could scale it in if you want, but these are actually equivalent, so I'm going to leave it like that. If you scale it in, you just get like this kind of slop fest, if you will. But I'm just going to keep it like that. And now we're going to take a look at something else that still kind of has to do with vectors, well, unit vectors in particular. It's a way to kind of standardize and actually look at a different type of notation for vectors. It's very similar to component form as it turns out, but let's take a look at that, and then from there, there's just one more topic to discuss after, and then finally we'll be done with 8.3. All right, so these are the so-called standard unit vectors, I and j. So they're vectors in their own right. I is the vector 1, 0, and j is the vector 0, 1. So these are the, again, so-called standard unit vectors. They point in the direction of the x and y axis respectively. In that alphabetical order, ij, kind of like x, y in that same alphabetical order, of course. And notice they're in the positive direction each. And as it turns out, every vector is just a linear combination of these vectors. Now, what a linear combination really means is something times 1 plus something times the other. So when I say something times, I'm really talking about a scalar multiple of 1. So really what we need are scalar multiplication and vector addition. Once we have those, then any combination of scalar multiplication and vector addition with these, which is called a linear combination, can actually define any vector. So as a result of this definition of for I and j, a vector v whose components are v1 and v2, well, you can write this, of course, as the vector v1 comma 0 plus the vector 0 comma v2. And notice if you scale out v1, I don't need the hat here actually, there we go. So if you actually scale out v, because v is just a number, this is 1, 0. Similarly here, if you scale out v2, this is 0, 1. And what you'll notice is that this guy here, 1, 0, the vector 1, 0 is just I, and this is just j. Now, of course, they're vectors, so I really should be putting the hat, but that's fine. So really what we can say is this is v1 scaled to I plus v2 scaled to j. So this is known as a linear combination of I and j using v1 and v2 respectively. So it's just a different way of writing a component form, and you can kind of jump to this right away if you're given this component form. And in this example, we want to write this vector u that goes from this point to that point as a linear combination of these two. So all I'm going to do actually is just write this in component form first. So notice that u is literally just in component form. Remember, the one we're going to minus the one we're going from. So that's a -1 minus -2, comma, 3 minus 5, just like that. And we end up getting -1 plus 2, which is +1, and then that's a -2, of course. So this is in, again, the standard component form, and we can write this as a linear combination of I and j quite simply now as just 1i, which is just I itself, minus 2j. So I hope we see how I'm getting this. I'm just looking at these and multiplying them to I and j in that order. So you can consider this to be the I component and the j component, if you will. Kind of like x and y, like I was talking about just now. So now the last idea we need to talk about has to do with angles, which is finally looking at the direction of a vector. So the magnitude is only what we've been talking about really a lot, which again is the actual length of the vector. The direction of a vector really has to do with its angle, so it's only fair we discuss angles. So let's take a look at that right now before we finish off 8.3. Alright, so as far as directed angles go, there's actually quite a bit we can discuss here. So let's first consider the vector a comma b in component form. And if we draw it in standard form like this, a standard position, meaning that it starts at origin, of course, we'll define the angle theta to be the angle from the positive x-axis. So here I'm considering A and B to be in the first quadrant, but it could be in the second, third, or fourth quadrant as well. We'll just again take the angle to be from the positive x-axis just like usual, like we saw in previous chapters, of course. Now, one thing we'll notice is that this distance, of course, is going to be A, this distance is B, and this distance is the length of V, which is the magnitude of V, according to the language in 8.3. Okay, with that being said, we can actually find cosine and sine of these angles. Notice cosine will be A over the magnitude, so we can write cosine theta as A over the magnitude of V. Really, if you multiply both sides by the magnitude of V, you get that A is equal to the magnitude of V times cosine of the angle. Similarly for B, well, notice that sine of B will be B over the magnitude of V. So if you multiply both sides by the magnitude of V, you get B is equal to the magnitude of V times sine of the angle. And combining these into our component form, we can see that V really is the magnitude of V multiplied by cosine and sine. So if you want to factor it out as a scalar, let's do that. And then you get cosine for the x value and sine for the y value. Let me scoot this over a bit. Now this is actually pretty simple to explain. This right here, if you think about it, has to be a unit vector. So this is some vector u whose magnitude is equal to 1, which makes a lot of sense because if you take the magnitude of both sides, magnitude of v must be equal to the magnitude of v times 1, so that means this vector must have magnitude 1. And what also makes sense is that this component vector here, cosine theta comma sine theta, is some vector that lies on the unit circle because its magnitude, of course, is 1. So there's a lot of relationships going on here. Now, this doesn't actually help us to find theta too much. It kind of does a little bit. But something that will help a lot, I think, is considering tangent. Because tangent actually doesn't, well, it kind of bypasses the magnitude. Because it's really just looking at A and B. Here we're asked to find the directed angles. Knowing tangent will only help. So let me just say, furthermore, so let me just say this implies that tangent theta, of course, is equal to opposite over adjacent, so it's B over A, which is, of course, well, we know actually that if we write it as this, the magnitudes will cancel and we'll just get sine over cosine anyways. So that doesn't really matter because we know that that's true, of course. So that may make you feel happy, but really what we need is this right here. So the tangent of the angle is going to be B over A. There's a little bit of an issue though, and the issue is that if you use tangent inverse to find theta, it really only works in the first and fourth quadrant because of the way tangent inverse is defined, but at least that'll help you find the reference angle. So let me just say here that, let me border this off a bit. Let me just say once again, theta equals tangent inverse of B over A is the calculation of the reference angle. So really I should call this theta bar. And the reference angle again depends on what quadrant you're in. So now let's take a look at this. And we can actually graph this to get a better idea as far as what quadrant we're in. So to graph this one, of course, 3, 3 for I and j, getting used to that ij notation. That's going to be here in the first quadrant. So to find its angle, all we need to do is consider tangent inverse. Tangent inverse of the second component divided by the first component is known as just 3 over 3 is 1. Tangent inverse of 1, of course, is pi over 4. Or 45 degrees if you like. And in the first quadrant, 45 degrees is the same as its component, its not component, but the same as its reference angle. So that will indeed be our angle here. Not too bad. Now this one is a little trickier because here we have to consider something different. So notice here the x value component was 3, the y value component is -4. So we're going to get something down here. Now this is our angle theta. Now really our angle theta should be considered from the positive x-axis this way. So the way I drew it down here is kind of like a negative value. So if you actually find tangent inverse, that'll give you the, you know, I kind of misspoke here. I should have said absolute value of, because tangent inverse could be negative since it could possibly be in the first quadrant or fourth. Remember that the range of tangent inverse is between -pi/2 and pi/2. And for that reason, it could result in a negative. But the reference angle is never thought to be a negative. Angle is thought to be only positive. So in any event, let's just get to it and actually find theta, which I should have wrote here, to be the absolute value of tangent inverse of -4/3. Now remember, this really is a calculation of theta bar, but here theta bar is actually equal to theta because we're in the first quadrant and we don't even need absolute values here. So here the calculation was a little less technical, but here it's a little more technical. Now, of course, at this point, we're going to have to use a calculator, so let's approximate and see what we get. So my calculator gave me about 53.13 degrees, something like that. Now notice that we don't actually need the negative because tangent inverse is actually odd because tangent's odd. So we can pull the negative out and then the absolute value of the negative goes away anyways. So really you can just do tangent inverse of 4/3, just looking at the absolute values of the components. Do the second over first. And then tangent inverse of that will give you an angle in between 0 and 90 because again we're taking the absolute value of it. But again, that's the reference angle. So we found out that this reference angle here has to be 53.13 degrees. That's fine. But what about this whole entire angle here? Well, in this case, the complete full rotation will give you 360. So 360 minus this is going to be our actual scenario here for this quadrant. Depending on which other quadrant we're in, we have to do a similar or a different calculation. So in the first quadrant, the reference angle is itself. In the second quadrant, it's 180 minus the reference angle. In the third quadrant, it's 180 plus the reference angle. And in the fourth quadrant, it's 360 minus. So let me say the fact that we are in quadrant 4 here implies that we must write theta as being 360 degrees minus theta bar, which we just found. And that is approximately 360 minus 53.13. And let's see if we can do this in our heads a little bit. So 360 minus 53 is 307, so it's going to be just shy of that. So it's going to be 306.87. Awesome. So that's the angle again from the positive x-axis around. So we use the fact that it's in which quadrant by plotting. And then from there, we can take tangent inverse of just the absolute value of the quotient of the second over the first components, and then from there that'll give us the reference angle and we do a calculation depending what quadrant we're in. So I hope that's not too bad. In fact, that's all I want to say finally for 8.3. So in the next section we'll be talking a little more about a vector still, and then in 8.5 and 8.6 is where we start to relate them to something that we saw in the past in algebra, just a little bit in algebra 1. So that's going to be interesting. In fact, that's a really big highlight in mathematics. So this is all building up towards that, because I know this may seem like a sudden shift in the class, like what are we doing? It seems way different. There are still some ideas that are similar, but it still has a different feel to it. But again, we'll kind of relate them and it'll be actually pretty nice. So I'll see you in the videos for that. Thanks for watching. Hope you enjoyed, and I'll see you then.